Okay, in the previous video we just derived this result here. We are now going to go back to our deriving the asymptotic approximation of this integral as lambda goes to infinity. So I've already mentioned that major contribution is going to come from the stationary point of this function called the stationary phase. So let's imagine that T naught is the stationary point of phi. So let's T naught be let T naught be a stationary turning point of phi of t, which is in the interval a to b. So then we are going to expand both f of t and phi of t in Taylor series about T naught. Okay, so expanding f and phi about T naught is now going to give us the integral from a to b of f of t. So this now is going to be like the integral from a to b. F of t naught here will just take the leading order term, then exponential of I lambda. We're going to have phi of t naught, and then this is going to be 1/2 t minus t naught squared second order derivative at t naught. If we just take those two terms, then this thing is going to be f of t naught e to the I lambda. Let's call this one phi naught. So this one phi naught, and let's call this one phi 2. Then that's going to be the integral from a to b e to the I lambda over 2t minus t naught squared phi 2 dt. Now there are two cases here. The second order derivative may be positive, or the second order derivative may be negative. So we're going to take the option where the second order derivative is positive. Okay, so we are going to let u squared be equal to lambda over 2 t minus t naught squared phi double prime at 0, What this means is that u is going to be t minus t naught. Then here we're going to have lambda phi 2 all over 2. So this is going to be perfectly okay, because this term is positive, this term is positive, and this term is also positive. So dt is going to be du times the square root of 2 over lambda phi 2. Then the integral becomes, let's call it I. So the integral I becomes f of t naught e to the I lambda phi at t naught. We're going to have integral from a minus t naught times that square root to b minus t naught times that square root term. Then we're going to have e to the I u squared square root 2 over lambda phi 2 du. And then if we since the contributions, the major contribution to this integral is going to be from the neighborhood of the stationary point, we can actually adjust the integration limits to minus infinity to infinity, e to the I u squared du. And then this integral is just the integral we derived a while ago. So we know the value of that one, so we're just going to plug it in, and then we have the value of this thing. So this is going to be f of t naught e to the I lambda phi of t naught square root of t 2 over phi double prime. Then this is just going to be square root pi e to the I pi over 4. And so finally this is going to be f of t naught e to the I lambda phi of t naught, and then we're going to have square root 2 pi here over lambda phi double prime. Then this is times e to the I pi on 4, which if we like we could write next to that one there. So this is for the case where the second order derivative is negative. The other case, which I am going to ask you to work through, is if the second order derivative is negative, then what we do get, do please confirm this by working through, then what we get is f of t naught exactly as before, e to the lambda phi of t naught times I here. So this is I lambda that minus I pi over 4 for this one. Then this is going to be square root 2 pi over negative lambda phi double prime. Now, so if this is negative, the negative of that makes this whole term positive. So we can generalize. So hence, in general, so our integral will take the following asymptotic function to leading order. So it's going to be e to the I lambda phi at t naught plus or minus I pi over 4 times the square root of 2 pi over lambda magnitude of the second order derivative, where the sign of the I pi over 4 agrees with that of the second order derivative. So if the second order derivative is positive, there's going to be positive here. If the second order derivative is negative, and that is going to be negative there. Okay, so that is our formula there. You're going to notice that it's well, structurally pretty similar to the one we derived for Laplace's method, except of course for the complex or the imaginary parts that it has. So in the next video we are going to look at some examples of the application of this formula here.